Okay, so welcome everybody. Thank you for joining today's call. Today's webinar about tunneling. My name is Wouter Nijsing and I'll be presenting our webinar for today. So thank you for joining on behalf of SAALG Geomechanics. For those of you who have stayed around a bit longer already, you know that this is the second webinar in a series where we present you our geotechnical platform Daarwin and its various applications. In the previous webinar that we organized, we covered an introduction to the Daarwin platform in general and showed you two specific case studies about the construction industry. Today, we will be taking it to the next level. We will be covering our next topic, which is all about underground construction and tunneling. And before I dig into the matter, into the details, I would like to extend a word of appreciation to our esteemed partner, Ram Katsis. We are organizing this webinar in collaboration with them, and we are working together in the various regions. They have a great track record and significant expertise on tech software, and they have a great reputation on local knowledge in the various regions, such as India, the Middle East, and Southeast Asia, which are exactly the regions that we will be covering today. Some short housekeeping rules. We are with many today, so you probably noticed already that your camera and your microphone are switched off. They should be switched off. The presentation will take about 30 minutes, and at the end we will have time for questions as we have time for a Q&A session. So what you can do, if you have a question, you can leave your question in the chat box, and we'll moderate it towards the end. Also, last note is that this session will be recorded. Great, so let's get started. The question that you may have is, why do we host a separate session on tunneling and underground construction? Well, I'm sure that most of you, maybe everybody of you, knows that underground construction is on the rise. We have seen several impressive projects. For instance, some that you might recognize here on the screen. In Hong Kong, the Hong Kong-Macau bridge link, with a part of that project being an immersed tunnel. And in Singapore, for instance, where the Circle Line and Downtown Route Metro are being extended. That's just a short example of underground construction and tunneling. In general, we see various trends that account for the rise in this industry. There's many, but I'll only focus on these three for now. The first one is definitely a very important one, and that's urbanization. More people start to live in cities. Cities therefore become denser, they become larger. And to meet the demand of all those people traveling into urbanized areas for commuting, for travel, or leisure, underground transportation is an integral part of the solution. That means that we see all sorts of underground construction and challenges, ranging from tunnels for transportation networks, metros and trains, but also tunnels for water and sewage networks, or even parking facilities and underground commercial activities. Furthermore, we see that the technology is advancing. So TBMs, for instance, do a part of this work. They do a great job and they become better. So they become more available, they become more efficient, and therefore they become more available to the market to deploy them on these kind of projects. And lastly, we see that the project scale is increasing. So new projects arise where the project scale is larger than previously constructed. So I can name many underground construction projects in, for example, Qatar, the Doha Metro, in Saudi Arabia, Jubail and the Riyadh Metro. And in India, we see several projects such as in Mumbai, Chennai, and Delhi, as well as in Singapore, Jakarta, and the Ho Chi Minh Metro lines. So that's great. The market is on the rise, and that's good news. However, there's a significant challenge. The projects that are carried out in tunneling specifically, worldwide, 30% of the cases experience cost and or schedule overruns that has a geotechnical origin as laying at the base of the problem. It's not a small deviation. We see that it accounts for more than 55% deviation from the original budget. So that's a significant challenge that is at stake here at the industry. It's not us claiming that. We have the links and the references laid out at the bottom of the page, and you can see those for yourself. So in short, the budget, schedule, and safety of tunneling projects and underground projects is a challenge. Now, that is where Daarwin comes in. Daarwin is a cloud-based platform for the geotechnical industry. And our tools, they can be deployed throughout the entire project and asset lifecycle, starting all the way in the planning phase. Daarwin is a system where you can mix and match the different modules that you need for your project, and also only those projects that you will use. So you can use these different systems. For instance, if I walk you through it really high level, in the planning phase, you can digitalize your entire project. In the design phase, you have very rapid and very advanced tools at hand that allow you to design better, faster, and understand better what's going to happen on your actual construction. During the construction phase, we have tools that help you to stay in control of your project, to understand what is actually happening on site. And even after completion, we have several tools for the asset maintenance and inspection market. Daarwin is a platform that can cater to different markets and different industries. For instance, the construction market that we covered last time. And today we'll be focusing more on the tunneling side of things. The clients that we work with are various. Because Daarwin is a very versatile platform, we work with various types of clients, ranging from engineering firms to general contractors and asset owners. And I'm sure you see some familiar names on here as well in each of those categories. So if we talk about underground construction, where Daarwin is applicable to be deployed is the following three cases. In the first place, we have the more traditional cut and cover type of technology. It's a conventional underground construction method. The second part is a specific TBM solution where we deliver a real-time model that improves the TBM operations. And the last one is traditional tunneling, where it can be a combination of drill, blast, and boring techniques. Usually you recognize them because of their typical horseshoe cross-section. For today, I'll give you specific examples about the first two categories. So we'll dig into that in more detail later on. First, really briefly, what does Daarwin do? Over the entire asset and project lifecycle, what we do is we decrease the risk on your project and we increase the insight that you have. Therefore, you have different modules that throughout the entire lifecycle you can deploy. And one of the tools that I want to focus on with you today in more detail is the back analysis. It's a really powerful tool. You see it as the fourth column. It's a really powerful tool, and I would like you to explain more about that. So in general, if we take a look at how the back analysis works, you need two things for it. You need, when using it in Daarwin, you need to have a Fluxus model, and you need to have monitoring data, or you need to have design criteria that can give you that same input. You put that into Daarwin, and then you start to generate your initial generation. That means that you start to generate various numerical models, and we start to compare them with the error that they have compared to, for instance, the monitoring data. Then we see how fit they are, so how well they fit. And ultimately, we select the best performing, let's say 10% of them. We reproduce that, and that forms the input for the new generation that again goes through that cycle. After a certain amount of runs, or after the model is optimized, you have your final outcome, which is an optimized model and optimized parameters corresponding more closely to reality. Okay, so I'm going to make that a bit more visual, and this might get a bit technical. I know that we have quite some technical people on the call today, so maybe it's not a problem. If this is a bit too technical for you, no worries. We'll be back with you in just a minute. Because what you see here is a visual representation. So it's a plot representing unloading and reloading conditions, for instance, used in hardening soil models. Where at the vertical axis you see the K0, it's the coefficient of earth pressure. So that's used often in underground construction, specifically for tunnels, because it gives you insight how the soil behaves under its own weight. On the horizontal axis, you see the reference modulus of elasticity for unloading and reloading of the soil. And that's a critical parameter because it's used in advanced constitutive models for finite elements analysis, like plexus, for example. Then you see the red dot on the screen. That serves as your, let's say, your monitoring input or your design criteria. And in this case, it's a synthetic case, and therefore we know the exact X and Y values. The lines that you see on the screen, they represent the margin of error, the morphology of error around that red dot. And what we'll do next is we generate models, so Fluxus models you could say, and we try to reduce that error from the model, meaning it will try to approach the red dot. So this is what happens if you generate your first generation. Every star represents a Plexus model, and every slide from now on that it will move on represents a new generation in the observational method to approach that red dot and reduce the error. So what you see is already in the second generation, it approaches that dot more clearly. And if I speed up towards the third, the fourth, and the fifth generation, you can clearly tell that the Plexus models and the estimations, they match the red dot much more closely, which means the error between the design and the actual operation has been reduced. Okay, now the reason why I bring that up is because that is one of the things that I will touch upon in the case study. The first case study that I will cover deals with a commercial building in Singapore. And this was a project that we did together for our esteemed client Kajima. I'm pretty sure you all know of Kajima Corporation. And for confidentiality reasons, I'm not revealing any more project or site-specific information, such as names or pictures. It is a good case study because we applied both the sensitivity analysis and back analysis. And the objective of the case study is to show you what kind of analysis you can do with Daarwin. So for context of the project involved a commercial building in an exclusive area in the central eastern part of Singapore. And the area is very much known for its lush greenery, for its proximity to schools and to transport links. And one of those transport links is strategically the MRT subway station. And the project wanted to respect the above ground natural environment, and therefore it needed to construct in the underground. Now, at the second picture at the right, you already see those metro lines, those tubes. So that is one part of the project. At the left side, you see a top-down view of the construction and excavation site with the two sections in more detail. On the top right, you see section 1. The left part there in the underground, that's a subterranean structure used for transportation and parking. And the second section, as I said, that's the tunnel cross-section. Now, in this webinar, for time and for, let's say, the scope that we have available today, I'm only going to focus on section 1. And I'm only going to focus on the behavior of one inclinometer. You see it listed there on the screen as well. In reality, many more instruments were used and many more, let's say, tools were used as well. So please keep that in mind. So in this use case, we'll take a look further at the behavior of the inclinometer that was installed and how it relates to the design. The excavation phase for that section 1 was as follows. You see that these 4 different phases. There were a few more, but these were the most important ones that we'll highlight. You see L1, B1, B2, and finite excavation level. And B1, B2, and finite excavation level are the ones that we'll be looking at more closely. So what we see here is a screenshot from Daarwin, where we see the plotting of the design values versus the monitoring data. Now, when we're plotting the design's displacement over depth, you clearly see it visible that the monitoring data and design have a discrepancy. And the 3 lines at the right, the orange, purple, and blue ones, those represent the design values. and the one more in the center represent the monitoring data coming in. So what happens is that then we ran the back analysis. The first graph that you see has the design value again at the right and the monitoring data with the margin of error, a buffer margin at the left. And what you see plotted in with the thick orange line, that is an optimized back analysis. So that is, let's say, our outcome of the model that tells you, hey, we actually have a much better design value for you. So with this information used in B1, we do not only update our design values in B1, but because of the updated parameter set, you also see that the design values in phase B2 and even the finite excavation level improve. In the third graph, you see here where we plot all the individuals. And indeed, you can clearly see how the model has improved, not only the orange one, but even the purple and to some extent also the blue lines. Maybe focusing slightly more on the buffer. So the buffer represents the accuracy of the instrument, but also the quality of the technician. So that's a subjective element, and the user has to interpret, so the geotechnical expert, for instance, has to interpret and define how large that buffer needs to be. In this case, you see that we ran almost 4,925 models, and 4,400, a bit less, were good individuals after 50 cycles of that back analysis. Then if we also take in information from the phase B2, we see a similar pattern. In this case, we again have an even further improved model for your B2. And as we see, the finite excavation level also improves. In this case, more than 5,400 models were run and 4,900 were good individuals. What you might notice is that the number of individual runs remains fairly stable to some extent. And that is because the search pace remains the same. So we're still optimizing for the same parameters. And the last phase is where we also include information from the finite excavation level. And there you see that indeed also that blue line, all those blue lines, they are improved significantly, which tells you that you can update your design parameters. One of the interesting parts in this case, I think, is that even with the information from the site of the first excavation phase, B1, you can already tell that the other elements for B2 and finite excavation level also improved. So what this tells us is that thanks to these types of tools, companies like Kajima, they can significantly improve their projects. Just imagine what it means for the costs on your project if you can design more efficient and you can design lighter. Think about the time that you can save if you can run these type of analyses in less than 8 hours. And lastly, also the safety element of your project. Knowing better how the ground is going to behave when the project moves from the design to the construction phase is crucial in these type of underground constructions. So now I want to show you our specific solution for TBM machines, and this is called Daarwin Gemini. This is a more recent development, so I'm really excited to show you this today as well. What we see here is that the International Tunneling Association indicates that since 2012, each year TBMs excavate more than 1,000 kilometers of tunnels. So that's really significant. So again, this is one of the reasons or one of the claims that we have to back up the statement that indeed we see tunneling is on the rise. Again, that brings us back to that same problem that I presented in the beginning. The geotechnical component of the challenges that tunneling projects face is significant and it needs to be dealt with in terms of cost, in terms of schedule, and also in terms of safety. Again, you can find the links of the numbers that we put on the screen here at the bottom. So what we did is we developed Daarwin Gemini, which is a software, and we developed that in collaboration with Acciona, the famous Spanish general contractor. They saw a need for it, and together we decided that ultimately we want this technology to reach the market. Therefore, we can present it here today as well as a solution for you and the industry as a whole. What Daarwin Gemini does is a few things. In the first place, it predicts the TBM advance rate. And in order to serve the operating team, we can check the data every 5 seconds. That means that we can deliver real-time insights or near real-time insights. That allows us to detect geotechnical anomalies in advance in order for the operating team to respond to them. So they have information at hand much earlier than they typically would. That means that it's also specifically a tool for those in the TBM operation team, either on the machine or let's say in an office or on site. What we're ultimately doing is working towards a platform to analyze different types of machines and different types of soil conditions. Now, what Daarwin Gemini needs is the following. The technical setup is slightly different than the regular version of Daarwin, where, for instance, we connect to an inclinometer that I just explained you. For Daarwin Gemini, you need to have access to a place where the data from the TBM sensor is coming in. So that can be a portal or it can be a project clone. We can work with different types of data and different types of file structures and formats. But the important part is that it comes in frequently for us to process it frequently as well. It is, by the way, compatible with various types of TBMs, so open shield, single shield or ripper, and closed shield, EPB and slurry machines as well. Contrary to the regular Daarwin system, in this case, you don't need a practice license for these types of operations as we calibrate the models on our own. So how Daarwin Gemini works in general, if I take you through the steps, is as follows. First, you need to have a geotechnical baseline report. That data we put in the black box, and then our Daarwin system starts to work for you. We need measuring data coming in from the TBM machine. And as a third step, we build a model. Now, the fourth and last step then is that you operate the machine, operate the project, and we compare the advance rate with anomalies and update information on the predicted advance. So let's take a look at what that looks like in more practical terms. I have a few screenshots of the tabs that we have available for the Daarwin Gemini system. So the case that I'm going to show you, again, for confidentiality reasons, it's anonymized. So the names and values that you see, they're completely hypothetical. The first step that we cover is about the advanced model prediction. And at this tab, you get an overview of the key 5 parameters. So this tab would typically be used by a project manager or a project engineer on shift to review the project progress. What you see is that we focus on 5 key parameters. In the first place, those are the inputs from the TBM operator themselves, or that they can influence at least: revolution, thrust, and screw conveyor speed. And subsequently, we also look at more observations. Those are the parameters that the TBM operator cannot influence directly. It is relevant, though, for the functioning of the machine and the project, but in an indirect way. And that is the advance and the torque of the machine. Now, what you see in the upper left graph is a representation of 5 rings. You see 5 horizontal sections. The orange bar there is the predicted advance, and the black line is the actual advance. So that tells you something about the quality of the model versus what you are measuring. For the model to start generating insights, you need about 200 rings, depending on the complexity of your soil conditions. And then at the upper right part, you see the main drive. There you keep an eye on all the key parameters over time. The bottom left one represents the excavation chamber and the screw conveyor. This one is important because for instance, high pressures give you the risk of rising or lifting the surface, and low pressures, they give you a risk of surface settlements or sinkholes. And at the bottom right, we see a more detailed understanding of the pressure at the front and at the back of the shield, the speed and the torque, and how that develops over time. The second tab is a tab used for a pilot assistant. So this is really typically used for the operators running the machines or in the operational team. What we see here is that in the first row, those first three graphs, what they represent, or what the question that they pose is what affects the advance. So you see the three different individual parameters, thrust, revolutions, and screw conveyor speed, because they are all inputs that can be changed by the operator. Then in orange, you see a line that represents the model prediction and the real-time input. And the black dots represent the actual performance. The green line then represents, if we focus only on that parameter, what would be the optimal condition. So it tells you something about how much room for improvement does the operator have to improve on that part of the TBM operation. The bottom graph that you see, sort of row 2, that is that basically asks the question, how does the input evolve in real time? So you can track the progress over time, again looking at the key parameters, thrust, revolutions, and screw conveyor speed. Then the bottom part, you see the advanced predictions of the observational parameters. So do the values really stay within the expected safety margins? The first graph that you see at the left is the orange part there is a model calculation to predict the advance minimum and maximum rates, and it generates 2 dots for every advance. The second graph on the right represents the chamber pressure versus the advance. And yeah, it checks if the reason that one is a stable box or horizontal box is because those values are predefined with minimum and maximum values. Now, the third tab that I'll show you is a tab on the TBM and the geotechnical side of things. And here in this view, what you see is how the geology is expected to change and expected to change as you will move forward. So this comes from the design and the technical report. And based on the specification of that report, we know if we have some type of friction, permeability, stiffness in the rock, RMR, etc. Now, what you, for instance, see in the red circle is that the geotech prediction is we will experience high RMR, and indeed you see that the actual situation is that a bit later we were experiencing that high RMR indeed. So the last step that I will show you is the human element of let's say tunneling operations. If you take a look at the entire project, actually only 30% of the time the machine is actually excavating. So it's important to understand the other 70% of the time as well. So for instance, if there is plant maintenance or if there's other types of preparations, shift handovers, etc. So even more important is to understand, was the delay foreseen or not? And the operator and the project team, they can indicate that here. This slide, for instance, or this representation tells you more about the time needed per ring. So for instance, around ring 715, you clearly see lots of delay. Therefore, it's important to know if that was foreseen, what the underlying causes were, and if it can be prevented or mitigated in the future. Now, I'll also show you one case study for this. And this was a specific project in Spain, in the northern part, in Mularoy. What we did here is, again, we operated together with Acciona. And the project initially started until 2009 as a conventional drill blast tunnel project with a small diameter, 3 meters more or less. And the stretch was a bit over 12 kilometers. And the reason for the project was to transport water between 2 rivers. Now, from 2017, the scope was modified and the TBM was deployed. That was a Herrenknecht single shield TBM. And later, the Daarwin Gemini system was developed in collaboration with Acciona as they saw a need for it. And this project was used as a use case. So the starting point for to train the data was about 6,000 rings worth of data. 75% of that data was used in the data set, and 25% was used to test the model against data never seen by the model. If we then do fast forward to the results, what were we able to do in this project? Well, we see that based on the results found in the case study, we were able to conclude quite some things. If Daarwin Gemini were to be deployed for the entire length of the tunnel, the TBM performance would have increased 12.5%. That is significantly, because that means that the time reduction, so the actual operating part, would have been shortened by 14 days. At the bottom line, that has a specific cost-saving effect of 1.5 million euros in this case, for the reduced period of the operation of the TBM machine, but also the subsequent equipment needed. And lastly, since there's less energy needed in those days, non-operational, you also reduce the energy needed for the project. So that means that you could save an equivalent of 140,000 tons of CO2, which is about 28,000 petrol cars on average, what they emit per year. So in short, Daarwin Gemini is able to deliver very concrete project benefits for clients and all the stakeholders involved. Okay, so that brings me to the final part of this webinar, and I would like to take you along the picture of what's next. Well, as I mentioned in the beginning, at SAALG Geomechanics, we continue to develop new products and expand to new markets. Last time we spoke about Daarwin for the construction industry. Today we covered Daarwin for underground construction and tunneling. And the next time we will cover Daarwin for the mining industry. So if you want to stay informed on that, make sure to follow us on LinkedIn and register for the newsletter to receive all the latest information. Great, that brings me to the end of my presentation today. Before I close off, I want to once again thank our partner Ramkatsis and in particular Meda and Jitendra in their support for organizing today's webinar. If you would like to contact us, you can see our emails listed out at the bottom, and you can also scan the QR code if you would like to book a meeting with me directly. For now, I would like to thank you all for joining, and I suggest that we open the floor to see if anybody has any questions. Let's see, I'm going to first quickly scan through a couple of questions. So which TBM prediction model CSM Gearing is used for the analysis of the penetration rate? So everything that happens, let's say, in the analysis part of the Daarwin, that's sort of the black box. That's where the magic happens, really. So that part I cannot share too much information about. As I said, the important part is that we have access to the real-time data coming from the machine. If we cannot tap into the data from the machine, sometimes there's a clone of data that the project team has that we can tap into. And an alternative is that we have reference information or reference project. So for instance, what you can do is if you have a twin tunneling project where one TBM goes ahead, you can use that data to feed the information for the second TBM. So these type of twin tunneling projects are very suited for this type of operations as well. Another question, the model is calibrated based in the GBR, but GBR is not widely used, and in many cases the quality of the data is questionable. Is it possible to perform an ongoing calibration based in construction data? Can the system show the deviation from the GBR? Yeah, so it's important to mention here that the baseline report definitely helps in the setup of Daarwin. or sorry, in the setup of the Daarwin Gemini system, I should say. If that is not available, yeah, sure, you can still run the machine, but the predicted advance will be much more difficult. So therefore, we need those two things, geotechnical report and the real-time data. Or if that is not available, we can have information from a twin project or a clone project. That is sometimes the case. But the geotechnical baseline report is something that is needed. Yeah. So in this case, another question that we see, very good question, does Daarwin necessarily require a Plexus model as an input? Well, in the regular version of Daarwin, you do get the full potential of Daarwin if you upload a Plexus model. There are some elements that you can work without Plexus licenses, such as the entire digitalization part of ground information, such as the ground modeling part, the geotechnical data analysis. In this case, for Daarwin Gemini, you don't need a Plexus model, as we calibrate our own models. So in this case, for TBM operations specifically, you don't need a Plexus model to operate. I hope that answers your question. Let's see if there's any more question. I think that's all. I'll give you a few more minutes to see if there's more questions. Perfect. I see one more question coming in. Is traditional method can use this platform? Yeah, so the traditional method that I referred to, the traditional tunneling method, that often uses a combination of drill, blast, boring, that can also be used or can also be used for in Daarwin. In this case, because of time reasons, I didn't focus on that, but yeah, we can also provide solutions for traditional methods. So it doesn't necessarily need to be a TBM project, doesn't necessarily need to be a cut and cover method. Basically, lots of challenges and projects that deal with underground conditions is something that we can deal with in the Daarwin platform or Daarwin Gemini platform. Perfect. Then I think we will leave it with that today. If you have any questions later on, feel free to, indeed, as Jitendra says, thank you for doing so, Jitendra. Drop me any email. I'll get back to you. You can book a meeting, and then we'll get back to you as soon as possible. Thank you for your attendance today. It was a pleasure presenting to you. I hope you found it informative, and hopefully we'll see each other next time.